Okay. Good morning. I'm Jason Crusan from Human Exploration and Operations, and I guess I was asked to talk a little bit about the human side of the challenges of Mars and going to Mars. So I have a really brief kind of overview today, and then I'll just do some Q&A as well. So one of the things that doesn't work. Okay. We have the classic NASA squid chart that kind of showing all the different elements that are needed as we're going off to Mars. I think that the key point to start taking away, though, is in the past we talked about the work that we're doing with Station and obviously Orion and SLS and the asteroid mission and such. And one of the key elements that we're starting to now work on is also habitation as well. And what you're starting to see is all the different elements that we need to pull together for human spaceflight are starting to get there and are actually under development and starting to work with the industry folks as well. We talk about Mars as a set of key challenges. This is our challenges chart that we use a lot. And the thing is to think about is how difficult some of these systems are when you think about what we need to land as far on the surfaces of Mars, the 20 to 30 metric tons onto the surface, when we've only done about a ton or so to date. The long duration, 1,100 days in deep space, that's obviously a key challenge. We've done with Station continuous crewed operations, but we're a very basically transportation-centric architecture with Station as we have today. So we need to figure out how to reduce mean time between failure of systems and get reliabilities up and complexity down of a lot of this. And in a lot of those areas, and then with doing that, we need to look at all the different habitation systems that we have to actually advance. And I'll spend most of my time on that. So in life support systems, we're trying to increase reliability of those systems. If you know our Station systems, that they've been quite troublesome. People like to talk about technology readiness. We had high TRL technologies that went into the Station ECLSS system. We had many TRL 9 systems. Every single one of them failed when we got into space. And we're still struggling with some of those systems today. So how do we actually get those systems up early, the ones that are Mars kind of class systems, and actually test those in the space environment? Environmental monitoring, we're very supply chain centric on environmental monitoring. We do grab samples and liquid samples and bring them back and process them on Earth. We're not going to have that ability later. We also, today, we monitor for what we believe are the most dangerous compounds that could cause damages to crew. One of the things you see in long-running systems is you're seeing new combination of elements coming together and causing new chemical compounds to be formed. And we don't have the full spectrum of being able to analyze those. So our next generation environmental monitors, instead of picking the 30 to 50 likely things that we're going to want to monitor for, we want to have a full GC mass spec capability on orbit that will be able to process that capability. Crew health, if you look at all of our crew health systems, they're one of our largest drivers as far as mass in space. And we want to bring down the mass of those systems. But first and foremost, we needed smaller systems in Orion, and we're already underway in developing the new ones for Orion for the missions that will have just Orion. And then when we had Habitat, we also don't want to then go back to the same Station methodology and add the big, heavy exercise equipment back in there. But we want to have more variety of exercise equipment at that point. Even things like long-duration food storage are challenges. In AES, Advanced Exploration Systems, in my group, we're even looking at things like synthetic biology, vitamin storage over long periods of time. Past 3 years, your vitamin deficiencies in stored capsule form go way down. So how can you actually replenish those? We've looked at different food storage techniques in the commercial sector, and a lot of people can't get past this 3-year kind of barrier. Even air barriers, past 3 years, they're having challenges in the commercial sector as well. And then vitamin values dropping. So what we're looking at is synthetic biology-based approaches where we can store things in a quasi-spore state and actually activate it later and actually grow amino acid chains and everything else that you need at a later date. And there's a lot of promise in that area that we'll also see industry kind of taking up. Other areas like fire, luckily the largest thing we've ever burned in space is about 4 inches by 4 inches. I say luckily because we actually don't understand large-scale fire dynamics. And we are now getting the opportunity to go and actually demonstrate large-scale fire on a Cygnus series of Cygnus flights. The Cygnus currently on orbit has a Sapphire experiment in it. The next Cygnus launching will have another Sapphire, and then the next one after that will as well. And this experiment is looking at half meter by meter long burn samples and looking at large-scale flame propagation to understand does it even occur and under what convection and those kind of things does it occur in the worst state. We're going to follow that up with another 3-flight sequence on detection and suppression and cleanup as well, and actually get the end-to-end risk related to fire as reduced as we can. In recent years, we've done a lot of work with radiation protection on getting commonality of sensors in place. There is one group, and I say one group, it's kind of a team of folks at Langley and at JSC primarily, with a little bit of folks from Marshall as well, building the sensor suites that we need for human spaceflight. And we've conducted a whole series of flights on those next generation radiation sensors of understanding and characterizing what we're exactly dealing with. We've flown, the same group has been the ones worked with SORI, Southwest Research Institute, that flew on Curiosity, our instrument that's there. We've flown next generation instruments on station that are kind of the size of a USB stick that plug into our laptops. We had a derivative of that technology on EFT-1 on Orion's first flight and getting deep space data. We're building the next generation sensors for EM-1 and EM-2 as well. That'll fly on Orion. And in addition to that, on EM-1, we have another biological CubeSat payload, a 6U CubeSat called BioSentinel, and it's also flying the same radiation sensor technology into deep space. And we're trying to characterize in a very well-ordered fashion the radiation environments that our crews will see. And at the same time, then we have things like storm shelter technology and those kind of things that we're trying to learn from and model those into future habitation vehicles and obviously even our model validation for Orion's configuration for flight as well. So how are we going to actually progress in the near term is the question we get a lot of questions about. We've talked about this in a series of phases. We talk about the Earth reliant and proving ground phases, and then going into Earth independent. If you look at the Earth reliant phase that we're at with station today, what we want to be able to maximize our utilization of station with is testing all those exploration technologies. And we're underway now, and a lot of those ECLIS systems and a lot of things I just described on the last page of actually testing those in flight on station. Our plan is to have the full-up Mars-class systems, habitation systems, all the ECLIS systems on board before the end of currently end of 2024. So in the 2022 timeframe at least, to have an end-to-end test and continuous operations of that next generation ECLIS systems. That doesn't mean that we're going to fly a brand new ECLIS up to ISS. In some cases, some systems will be absolutely brand new. In other cases, there'll be an evolution of a system that just had minor issues on orbit. And we're making all those trades right now to figure out which ones do you do full-up systems for and which ones do you do progressions from current technology. All that will feed forward into kind of our proving ground phase 1 activities. The key part of proving ground phase 1 is obviously the flight test of SLS and Orion, getting those up there and getting operational experience on those vehicles and performance of those through the EM sequences. We use a kind of a pacing item in the middle of the 2020s, the asteroid redirect crewed mission, as a point where we've gone through enough validation that we can actually conduct a mission of importance, in this case the asteroid redirect crewed mission. And we're starting to moving more from validation to mission operations in that point in time. And then Proving Ground Phase 2 is where we start actually building out and validating the deep space habitation strategy and in-space propulsion capabilities to take us beyond low Earth orbit that will occur. Some of the flights of habitation elements will occur in this, what we describe as Phase 1 here. And we're kind of working through what that EM sequence of flights will be. That's just what our next step studies that are being conducted with industry are covering as well. But we want to move into this Phase 2 validation so that at the end of the 2020s, we have a full-up habitat capability with habitation systems and a propulsion system that is Mars class, meaning 1,000-day plus class missions with no interaction with Earth. And that's kind of when we know we're done with the Phase 2 activities, and then we can move on to, at that point in time, we could, in theory, go all the way to Mars and do an orbital type class mission. You could visit asteroids in a native orbit. You could go to moons of Mars kind of a class. We would not have surface systems at that point in time, but all the in-space type systems would be in place. So with that, I think I'm at about 15 minutes through, halfway. And so I wanted to just open up for questions that you guys have. That was probably more useful than hearing a standard NASA pitch, because I'm recognizing a lot of familiar faces in the room. So
if you have some questions, we have some guys here that they're going to bring the mic to you. If you do. I actually anticipate you might not. You might not want to ask questions sitting next to your competitor. But if you do, please ask questions. This is the place to make that happen.
Jason, just a question on the deep space habitat and ecosystems. Is another aspect that you might want to look at, like the effect of radiation on what's going on inside those systems, like microbial virulence and things like that, that might be different than what you're seeing on station because you're not getting the full radiation environment that you're going to get in deep space?
yeah, so all of our microbial work on station, this is a good point, and it's probably a nuance that is lost on most folks. There's microgravity effects and there's radiation effects. In the environment of ISS, we've never been able to separate on any of our biological virulence, all those kind of experiments, the effect of microgravity versus the effect of radiation. That's a true statement. So scientists can argue about which effect is the one causing it. But I have never seen a controlled experiment that actually separates the two. With our BioSentinel 6U CubeSat that we're building, it is a biological experiment. It's a representative yeast experiment, and it will separate the radiation effects from the microgravity effects on that strain. And then it's a model strain of yeast that we can then extrapolate the virulence into other strains. So on EM1, we plan to fly this 6U CubeSat. It is a modified strain of yeast that actually has DNA breaks that are repaired as a function of radiation exposure. So we can actually understand radiation exposure rates and virulence rates different from microgravity from the radiation effects. And at the same time, we're flying the same model experiment on ISS, and we're building the same thing on a Brookhaven experiment as well. And we're going to do variable levels of radiation exposure both on the ground with station and deep space in a very controlled way to actually understand for the first time microgravity effects versus radiation effects on, in this case, a model yeast organism. That should be able to give us some data to prove or provide data related to which is the contributing factor in a more systematic way. So.
Jason, just curious, what do you think the biggest technology gap is out of the different ones you went through?
Biggest technology gap. It really comes down to, it's not so much technology, it's our trust and reliability of technologies. Arguably, we could go fly a mission to Mars today with today's technology. It would be too massive. Because either the systems themselves would be too massive, or the number of spares that we would need to trust its reliability would cause the vehicle mass to go too large. So reliability and there's many different ways you can get at reliability. So you could just go on overall reliability of a system, or you could look at dissimilar reliability of systems. You could look at modularity approaches of avionics boxes. So there's many ways to get to an overall Mars system reliability. But I think that's the hardest piece, is getting to that overall system reliability to a point that we accept that risk without a vehicle so large that we can't push it out. And that's going to be the trade. Everybody said, well, you can just make your HAB this much larger. Well, then your in-space propulsion trade goes way, way up as well. And our pacing item for heavy lift launch vehicle, one of the primary pacing items is the in-space propulsion stage. It's one of the largest things that you don't want to have to assemble in space. So you can't break it apart and fly it in multiple flights. You'd want that as large of a chunk as possible, maybe with refueling or something like that, but that's one of the largest pieces. And then the other piece is the ascent vehicle off the surface of Mars is the other piece you don't want to have to assemble. Some assembly required for an ascent vehicle is not what you want to tell the crew. So. Yep.
Jason, just fast forwarding, we know we're in a presidential cycle, and in a few months you'll have to present to a transition team, on what your thoughts and intentions are going forward. Is NASA prepared to talk about a new architecture and mission and sell that? And do you plan to also engage with industry for a unified message in doing so?
So I think your first question, are we prepared to talk about a new architecture?
Well, the transition from ISS to cislunar.
Oh, okay. To talk about this transition.
Talk about that, yeah.
I think we are well positioned talking about this transition. I think one of the key things is that we want to communicate is not changing the architecture, actually. These kind of 4 to 8 year cycles of changing fundamental choices of architecture are a big challenge. I think one of the values, we talk about this from a capability framework. We used that terminology before, and we are building fundamental capabilities, in this case, a heavy lift launch vehicle that we know we'll need regardless of whatever missions that people want to complete. We know we need an ability to get reliably crew safely to and from deep space, and have safe haven capability for periods of time that to get that crew, hence why we have Orion. We know we need habitation, and we know to wherever we want to go, whether it's whatever distances we want to go. So we need, and there's a lot of commonality in habitation as well. And we know we're going to need in-space propulsion. So to me, there's kind of fundamental physics guides your architecture. Building these capabilities in an orderly fashion that fit within the budget is the other challenge. Yes, you can accelerate things, but that needs that you need to. When you start stacking development cycles on top of each other, then you need a budget. And I've never seen any plans that drive us to a significantly larger budget amount than what we've seen historically for human spaceflight. So. So if somebody came in and said, yeah, you want to move things to the left, great. Show us an actual budget commitment from the administrations and Congress. Otherwise, building capabilities in a systematic way in an orderly fashion, as we know we need them, is a way that we can actually meet the needs of getting into deep space with humans and being fiscally responsible under the realism of budgets we have. And that's kind of where we've driven out a necessity. So, and your second part was the industry piece. For the most part, I think there's been a lot of movement lately, and I read all your guys' op-eds and your guys' discussions, talk with many of you on a regular basis. I don't see wide variances in what we were talking about and what industry is thinking as well. We'd obviously all like to go quicker on schedules or do more development at whatever pace, and we wouldn't disagree with that stance. So I don't see like wide variances between industry and what NASA is talking. I think we're collectively talking with the same voice most of the time. So, yeah.
Am I allowed to ask a question?
Sure, Dave.
So given the criticality of reliable ECLS in cislunar space and the finite life of space station, in my mind, I tend to think about two types of ECLS on station. One is that's operational ECLS and needs to be held to the standards that that you need for human spaceflight, and the other is research ECLS. And if research ECLS is held to those same standards, maybe we can't iterate fast enough to make the progress we want. So I thought it might be interesting to hear. I think it would be interesting to hear your perspective on how to separate the two, so that research ECLS can have a chance to iterate. And
Yeah, so a lot of our technology demonstrations that we're doing today, I was talking about this GC mass spec kind of capability. We are building that not as a Crit 1 hardware piece, but as a technology demo, and that's why we're able to accelerate it quite a bit faster. And so we are taking the philosophy, let's get hardware up there quickly, get it into the environment, learn from the first one, because it will probably likely be wrong. We could have spent a lot of time on the first one and also be likely wrong, is the argument. And so let's go as fast as we can up on it. Where it gets into the complexity is there are certain station systems today that we like and they work quite well. We'd like to slightly modify those. So what does that mean to change out a sorbent bed in a CO2 scrubber on its Crit 1 certification? Well, if you have other means by which to achieve that functionality on station for a period of time with an ORU swap out or something like that, then you can still get to that rapid kind of deployment work. And that's the balance that we're struggling with, is how to do that in a reliable way without putting the station ops today at risk. But you also, a lot of ECLS systems are consumable based, meaning you want the other systems off and you want to run the new ones for a long period of time. Turning ECLS systems off is a challenge. Dormancy of ECLS systems, we're talking about bacteria and virulence and all those kind of things. There's some systems, once they're wetted, we'd rather never turn them off. That's just the functionality of the system. We'd rather just leave them running. So we're trying to work through those pieces. Right now we envision the equivalent of 4 or 5 racks of equipment that we need to test all of our additional ECLS systems. That does take into advantage of some of the existing hardware that's up there already and just modifying an ORU. But some systems will want to do other more significant changes to things like our oxygen generation assembly that we have up there. The only fundamental change for that system is we would no longer need the safety requirement of the hydrogen dome. Just because of the operational experience, we know that that risk was, we were being too conservative in the risk management of that. So do we need to fly a new version of that system? Likely not. We would just, the next time we go to build it, we would change the hazard control strategy on it, which doesn't affect its fundamental operations. So, any other questions or?
Hi, Jason. ECLS has always been at the top of the list, and you just said some things that are interesting in terms of the current ISS system, and you even referred to the sorbent beds. I'm also aware in the next step effort, you've got some ECLS providers that
Yep.
are working on that. So you've got this portfolio of ECLS that's sort of formed in different approaches, different providers. And how do you see that evolving in the future to a solution?
So it may be confusing from the outside. We have
Yes, it
3
is.
awards under Next Step. 2 of them are system level studies. The UTAS study is very much a modular approach to ECLS systems. Taking the knowledge we got from Orion and ISS, how would you make a more modular style electrochemical ECLS system? So it's a very conceptual study of how to make that more modular. The other study that we have in there is more biology-based ECLS. The inclusion of plant systems as part of your overall balance, and understanding what large-scale plant structures in space would actually give you or provide you. A lot of those old studies were in the late 90s, pre-mass adoption of LED lighting systems, and modern electronics and those kind of things. So plant-based inclusion in large-scale systems was never traded well. I would argue because of the system mass. And so we're reevaluating what a true large-scale plant system would bring us and what it would cost us to, and redoing that. The third is a study on an actual technology investment with Dynetics, and it's a CO2 removal system. So I did touch on sorbents. So CO2 removal is our most challenging. It's our most problematic system we have on orbit. It's one of the ones that most likely has the most direct impact to crew health, as we're finding in some of the data that we're getting, even from the eye challenges we're having. So CO2 is definitely on the top of our list. Sorbents is like one of 5 options we're looking at with CO2. So we're making multiple investments in CO2 removal options that we have right now. We want to see those options progress over the next 2 years or so. And in 2018, 2019 timeframe, actually look at what do we down select to actually be the final CO2 system. And it may not be a down select to a 1, it may be more than 1. Just knowing how much the current Seadra bid us, I would hate to down select to one option and then get it up to full scale flight and then get bid again. So we'd like to see carrying forward 2 options in that area. And we're kind of systematically going through every one of the ECLIS systems and looking at that. We're doing UWMS, Universal Waste Management System, the POTI, as well as a contract with UTAS that we just issued. It is a DTO flight demo that we're doing on ISS that will actually be the same waste management system that will fly on Orion on EM1. And as we're going to 7-person crew on ISS, having an extra facility on orbit is a nice to have as well. And we've had some issues with the Russian toilets over the years too. So we're systematically going through every subsystem in ECLIS and trying to come up with, it's not a one-size-fits-all strategy. CO2 is kind of an all-hands-on-deck kind of area because of the implication of it and the challenge of it. Other areas we know the likely solutions, and we're just kind of doing natural incremental improvements too.
Okay, and so you mentioned we got bit on ISS. That's a sorbent-based system.
Yeah.
But is that more on the system side of it versus the actual technology, fundamental technologies behind it?
Yeah.
Can you expand on that?
Yeah, so a little bit on the sorbents themselves, and then the system reliability as well. We've seen water where it shouldn't be. I happen to be the one that managed the Sabatier procurement with UTAS, and I know a number of our troubleshooting days were spent understanding why we were getting water in Sabatier when we're only supposed to be getting CO2. So that's obviously a system error that's occurring upstream from Sabatier. So it's a combination of both of those. And there's actually some good papers out there that people have published about Seadra performance and those kind of things. So I'd point you to those for the more detailed technical work.
So Jason, when you say we, I mean, that's a big word, and I'm curious, really for my own information, how do you decide what NASA, can you just talk about your thought process? What does NASA do? What does NASA go and look for? What do you expect maybe from industry or academia? How do you think about that portfolio and how it's divided and how it'll be divided as we really solve these problems?
Yeah, so I say we, it's we, the space industry, and we is academia, universities, small business, large businesses, and NASA in-house. And we actually really pull on all of those elements to actually get done what we need to get done. So everything from SBIR type work that we do a lot of investment in SBIR every year. And that's technically under the hat of our Space Technology Mission Directorate, but we work really, really closely with that. So it is a portfolio approach. So when we look at CO2, we're doing a Next Step award in one area, we're doing some SBR investments in another area, we have some in-house work, we're getting sorbents from another industry base. So it is a portfolio approach of managing it by system or system functionality. So it's, and I would say it's highly tailored by the system and what the industry looks like for that system. So, and I think I'm out of time. Or unless there's one more.
Is mental health in your organization as well?
No, that's in our human research program. They're a sister organization in the Human Exploration Operations Group. So human research program, it looks at they look at all those, they have 31 trackable risks that they manage that are the human system risks and the mitigation strategies for them. They also own the kind of the crew health systems, technical systems like exercise equipment, for example. And even under that, they do a lot of the partnerships related to some of the plant growth work as well. So we do partner with them, I should say, but they own the mental health and the crew health overall research responsibilities. Okay, so thank you guys.